Alright, welcome back. In this video, we're going to go over pressure volume loops. As you may know, many things can go wrong in the heart. Physicians require tools like scans, tests, and graphical readings to assess the faults. One of these tools that physicians can use is called pressure volume loops, or PV loops for short. It is a graphical representation of the relationship between the volume and pressure in the left ventricle. So here's a picture of the heart. We are only concerned about this portion right here. This is the left ventricle. Remember, everything's reverse. We only care about the left ventricle because that is the chamber that's going to pump everything out to the rest of the body. It goes from the left ventricle to the aorta, and the aorta pumps everything out to the rest of the body. This is what a typical PV loop looks like, a very generic one, and that's what we're going to go over. But first, let's discuss why this graph is important. What can doctors conclude from this graphical representation of the heart? One thing that they can look for is something called dilated cardiomyopathy. It's when the heart is enlarged, specifically the left ventricle. And this can cause issues with volume and pumping the blood. Another one is aortic stenosis. It's the narrowing of the aortic valve, which can result in an increase in end diastolic pressure, which we're going to talk about. Another one is aortic regurgitation. This is when the aortic valve fails to close. And this would cause blood that's currently in the aorta to leak back down into the chambers. And there are so many other issues as well. That's why this graph is important. So here's the graph. We're going to take it really slow because, to be honest, this is the most dreaded subject or topic for most physiology students. They just don't enjoy doing this. And I can understand why. It's very, just graphs, okay? But yes, it is kind of annoying. So we're going to take it slow. So let's start with what we see, what's going on here. So this entire graph is only looking at the left ventricle. Nothing in the aorta, nothing in the right ventricle, nothing in the right atrium or the left atrium. It's all the left ventricle. And remember, the lungs picks up oxygen and puts into the blood. It then returns through the heart into the left atrium. Then it goes down, passes the mitral valve or the bicuspid valve, and it enters the left ventricle. In the left ventricle, it starts filling, and then when it contracts, the blood moves past the aortic valve into the aorta, and the aorta pumps it out to the rest of the body. So this graph is showing the relationship between volume of blood, which is down on the x-axis, and the pressure on the y-axis. So the easiest thing is to start from A, the bottom left-hand corner. The first thing you should notice is that we're starting at 65 for the volume here. It does not start at 0 because there's always some blood located in the ventricles. It is never empty, never completely 100% empty. So we start at some number. We are just saying it is 65 for this example. And just for clarification, it's in milliliters. I should have said that. I apologize. Okay, milliliters. Volume in milliliters, so 60 milliliters. So let's start with A. What is A telling us? Why is this important? A is telling us the mitral valve has opened. So let's write that down. Mitral, you can't see that. Mitral valve has opened. The mitral valve is the valve between the left atrium and the left ventricle. So what's happening is the blood from the left atrium is now dumping into the left ventricle. because the valve is now open. And we can see the volume is going up, right? We're going to the right. The volume is increasing. Notice that the pressure is still the same. We have not increased in pressure. Think about a water bottle. When you're filling up a water bottle, you're filling it up, but the pressure is actually not increasing. It's not until you squeeze the bottle is when the pressure increases. So imagine we're just filling up a water bottle. Just imagine that. So A prime here, what is that telling us? It tells us the mitral valve is now closed. So mitral valve is closed. Okay. Mitral valve is now closed. Now, after A prime, after the valve is closed, notice that we are still increasing in a little bit of volume, just a tiny bit. Some blood is still going in. But so now we're basically reaching maximum filling volume, basically, or end diastolic volume. We are done filling. As much blood has gotten into the left ventricle, we are done. So we notice an increase in pressure now. Valves are closed now. Both valves are closed. The aortic valve is closed and the mitral valve is closed. It's a closed system, essentially. We're going to increase in pressure. So B is end diastolic volume. We are done filling up. Done filling up. Okay. Now from B to C is very important. This is called isovolumetric contraction. So let's write that down. Isovolumetric contraction. So it's this right here. Or a little bit higher. I butchered that line. Okay, let me just do this. Okay, like that, and like that. Okay, that's called isovolumetric contraction. The reason it's called isovolumetric contraction is let's break down the word. What does it mean? Iso means same. Volume is volume of blood. And metric is measure. It's the same volume of blood, but we are contracting. So what is going on is that the left ventricle is contracting. But no blood is leaving yet. Because the valve, the aortic valve, to actually get to the aorta, which is the next step, is closed. So what is basically going on is the left ventricle is contracting and building up pressure. We are building up pressure because the aortic valve can only open through pressure. The left ventricle pressure must be higher than the aorta, then only the aortic valve will open. So we are essentially building up pressure first. So that can be shown with this straight upward trend here. We are increasing pressure. We're going from, what is this, like 30, 20 to 80. We are only building pressure, volume stays the same. Okay, now at C. C is the point where the aortic valve is now open. Aortic valve opens. The reason is because, once again, the left ventricle pressure is now higher than the aorta. And by laws of physics, we want to go from a high pressure to a low pressure. Blood wants to go there, wants to go towards a low pressure environment. So the aortic valve just swings open. This is called afterload. The term is called afterload. Now, at this point is when the blood will enter the aorta. So notice, we are now losing volume. We're going this way. We're going left, right? We're going from 135 all the way to 65, right? So we are losing volume. This is where students kind of get a little messed up here. It's because they see this curve here. And they're like, wait, what's going on here? Break it down into the axis. This is my tip here. Is first look at what's happening only in the horizontal direction and then look at the vertical direction. So let's look at the horizontal first. We are going from right to left. Higher, right? We're going from here this way, in this direction. Don't care about how high we're going yet. We're only going from right to left, notice that. If we go from right to left, we are losing volume. We're losing volume. Now let's only look at the vertical component here. We're going higher. We're going from this point in C to D. That's it. That's how high we're going. Don't look at the horizontal yet. Only the vertical. We're going higher. If we go higher, pressure increases. Higher pressure. Lower volume, higher pressure. So what's going on here? What's happening is the ventricles, the left ventricle is still contracting, but we're losing the volume now because it's going into the aorta. The ventricles are squeezing, still they are squeezing, and the blood is leaving the ventricles, so we're losing volume. But it's squeezing, so we still have pressure. We're still building pressure. Not as sharp as here. This was a sharp increase. Since we are losing volume, but contracting at the same time, the pressure difference is not that great, but we are still increasing in pressure. Stroke volume is the amount of blood that we lost in the ventricles through contraction. That's all stroke volume is. So let's write down what's happening. Ventricles contracting, blood leaving ventricles. And it's going to the aorta. Sweet. We're almost done. What about D? What's happening at D? This is called end systolic volume. End systolic volume is the point where the ventricles are done squeezing. They let go as much as blood as humanly possible. They are done. There is still blood left over. Remember in the beginning I told you that there's still blood in the ventricles. We cannot squeeze all of it out. It's not a perfect system. There's still leftover blood, but that's okay. As long as it's not like major. So it's called end systolic volume because the ventricles are done contracting. They're done. Whatever blood went out, went out. We're done. So it's called end systolic volume. And the reason is because ventricles are done contracting and all the blood that could leave left. Sweet. This is also the point where the aortic valve shuts. Okay. The aortic valve shuts, so no more blood can actually go into the aorta. We're done. Everything's shut now. The point from D to A is also very important. If this was isovolumetric contraction, this should be isovolumetric relaxation. So isovolumetric relaxation. Okay, which is from here to there. From D to A. So from D to A. What does it mean? Well, iso means same, volumetric means volume, metric means measure. It's the same volume of blood, but we're relaxing now. Okay? So the ventricles are relaxing. Ventricles are relaxing. Pressure falls because it's relaxing. No volume increase. The ventricles here at this point are not filling up. Everything is just fine. We're basically, think about equilibrium. We're not really in equilibrium, but pressure falls because our ventricles are relaxing. They're not filling up. They're not doing anything. They're just relaxing. We're chilling on the beach, for example. The reason they're not filling is because the mitral valve is not opened yet. Because remember, A is when it opens. If the mitral valve is not opened, no blood can actually get from the atria to the ventricles. So the ventricles are just chilling. They're just relaxing. And all of this is really fast, by the way. This graph makes it look very slow. You're like, wow, from here to here takes a long time. Remember, it's not time. Nowhere in this graph shows time. That's a common mistake students make. There is absolutely no time component at all in this graph. It is all about volume and pressure. So when people think, oh wow, this is a huge curve. No, it is, but nothing about time. It's just the relationship between volume and pressure. And so it's called a loop because we start all over again at A. And we just do the same thing over and over and over again. Forever, until you die. Let's do a scenario. What happens? What would this PV loop look like if there was an increase in venous return? So say if we are now dumping more blood into the left atrium, for example. If there's more blood in the left atrium, there's going to be more blood in the left ventricle. So what's going to happen? Let me draw over it, and then I'll erase it, just in case if you guys still want to read this stuff. Or you would just pause it. Okay, so if we had more blood in the system, in the heart, more blood coming in from the left atrium, from the lungs, we're going to have this, but we're going to go further out. Because you have more volume. The pressure's still the same. We just got more volume. And it's going to increase like this. And we have the same thing happening. And then it would probably look something like this. And we're going to go down like that. Just more volume. In this scenario, yes, it may take a little bit longer to fill up, but don't just actually forget I said that, because that has to do with time and you're just making assumptions. But I'm just thinking through, like medical stuff and whatnot. But yes, it looks like it would take longer, but really the graph is not showing that. What it is showing is we have an increase in volume. We started, the end here was 135, so now we're probably like 160 here. Pretend we're like 160. The pressure is a little bit higher. Notice the pressure is a little bit higher here. That we don't know for sure. But if you're given this question on an exam, you can play it safe and just say the pressure is going to be the same. Because we don't know. We really don't know. Unless we actually run the actual scan. But what we do know, just by logic, is that the volume would be higher. Because we are having more blood in our system. More blood's coming in, so more blood must go out. So that's what it would look like. And that is PV loops. If you found this video helpful, please like and subscribe. And until next time, later.